So thanks to hydrogen bonding of water molecules, water has attractions to lots of types of compounds. Water is attracted to other water molecules through hydrogen bonding, but also to other polar molecules or other ionic compounds. Water has attractions to almost all types of compounds. The only attractions it does not formally have is to non-polar compounds. So water can be attracted to polar compounds and ionic compounds, and that's the starting point of water being able to dissolve so many types of compounds. And it's called the universal solvent because it can dissolve polar compounds and most ionic compounds. So when water forms a solution from dissolving, a solution is a homogeneous mixture where you can't see the parts. So a solution starts usually with a solvent, which is usually water, usually some liquid or water. And the solute is something that's being dissolved. It's usually a solid, but it doesn't have to be. And there's usually just a lot less of the solute and a lot more of the solvent. So when you take a solid like this ionic solid and you put it into liquid water, what happens is that the water will surround the ions and separate the ions so that they are no longer attracted together, as would happen in an ionic compound. So the solid can be an ionic compound like NaCl dissolved in water, and you have an NaCl or salt solution. You can also have the solid as a polar compound like sugar. So sugar or sucrose, that is a polar compound C12H22O11. When you put it in water, the particles are polar and they also are surrounded by the water molecules and kept apart. And so, but you can have water dissolving, even other liquids can mix in with water, and this water can do this because it has all of those abilities to hydrogen bond with both polar compounds and ionic compounds. This in the replacement reactions, that if water is a solvent and the thing that is being dissolved is soluble, what you have is an aqueous solution. So when you have an ionic compound that can dissolve in water, it's soluble, and that's called an aqueous solution. This is showing the process of dissolving at the molecular level. And so if you start with an ionic compound like sodium chloride, this is the solid where the ions are closely packed together, they're not moving, and this is, you can see this solid. So this is in comparison to a sodium chloride solution where the ions are separated because water was added to it. So you add water, so here are the water molecules, and the water molecules will surround each individual ion. So here's a sodium ion surrounded by water molecules, here's a chlorine ion surrounded by water molecules, and here it is close up, that the ions, which would prefer to be attracted together because positive to negative, instead are attracted to water molecules. There's a little jacket of water molecules around each ion that keeps them apart from each other. So the ionic solid, when you add water to it, the solid is the solute and the water is the solvent. You end up with an aqueous solution. And those ions, which are the cation, the positive charge, and the anion, the negative charge, they are attracted to the water molecules surround each ion, and having those water molecules surrounding keeps those ions dissociated. They're separated ions. Okay, so now those are aqueous ions. And you don't just have NaCl, the entire compound together. In fact, you have the ions separated. You have Na plus cation separated from the Cl minus anion. So what you would write instead of NaCl as an aqueous solution is you can write the ions written out separately, the Na plus and the Cl minus. It's easier to see the process of dissolving at the molecular level in action. So this is again taking table salt, which is NaCl, and put it in water. Water is the universal solvent, and it's a very good solvent because it dissolves lots of things. In fact, water can dissolve so many things that it's never 100% pure. So that's where water quality and water pollution become an issue. So for any water, there's always going to be a lot of stuff dissolved in it. It's just a matter of how much. Like this is showing a calcium ion, magnesium ion, sodium ion. But also other types of, these are polyatomic ions. There's sulfate, here's nitrate. And they're not in there because someone purposely put these ions in the water, but it's just because water can dissolve so many things. And so water just naturally picks up these ions as it travels from its origin, usually a reservoir, to the homes where we are drinking the water. So water quality is tightly monitored, and it's thanks to the EPA, the Environmental Protection Agency, that protects our air, also protects our water sources. So anytime if you're thinking, oh, I wonder what's in my water, you can look up your water bill and find out the organization. If you live in Los Angeles, it's LADWP, that's Department of Water and Power, and there's an annual water quality report. And so these units are similar to air pollutants, where these are pollutants in the water, and they should be at low concentrations, which are parts per million and parts per billion. So these are parts per million and parts per billion are used for very dilute solutions when you have a very small amount of solute dissolved in water. So 1 part per million is 1 milligram per liter. So these would be parts per million: 97 parts per million, 51 parts per million, 27 parts per million. 1 part per billion is 1 microgram in 1 liter. And so we'll see that in a worksheet.